Welcome to my talk. I'm going to be talking about Corrosion, which is a distributed system that we built at Fly. So yeah, it's a spoiler, it's eventually consistent. It's fast because we prioritize speed, basically, is a choice we've made. So just a little intro. My name is Somtochi, as Ian has graciously introduced me. I'm a software engineer on the networking team at Fly. It might be a bit weird that I'm talking about distributed systems, but I'm on the networking team, which is not exactly the same thing, but I'll explain that later on during the talk. I'm based in Abuja, Nigeria, and of course, I'm interested in networking, distributed systems engineering. My last watch is Severance. I don't know who's a fan here, but this is my auto speaking. And I'm currently reading this very old book. It's written in like the 1940s on how to read a book, which is kind of meta. But yeah, just little things about myself. I also like rap battles, but I'm going to spare you guys the horror of listening to me rap this evening. What do we do at Fly? I'm sure there are people here that might be hearing about Fly for the first time. So basically, we make it easy for developers. We are a developer-focused cloud platform. And that means we make it easy for developers to get their apps deployed, up and running. But something I think that really differentiates us is that we make it easy to deploy your apps in different regions over the world. We are available in like 40 different regions, right? So it's basically like a CDN, but for your apps, right? You deploy your apps in different regions that you have the most users, and they basically get to access the one closest to them. So it's pretty easy. We make it very easy. You give us a Docker image, we transform it into a Firecracker VM, and we run it on our own hardware. It's also very easy to configure stuff like private networking, load balancing, scaling your app, all of that. It's basically takes out a lot of the ops in DevOps, I would say. So how do we do this, right? You want your users routed to the closest instance of your app that is running. So how does this work? This works because we announce the same IP address from different servers. We have like two types of servers. We call them edges, which are kind of the ones that interface with the world. So we announce your IP address from those ones. And there's this thing called Anycast. So if you announce the same IP, through BGP and the magic of the internet, your user will get routed to the one closest to you. It uses latency as a factor for selecting the best route. So our networking, so once it gets to an edge, the edge would route your request then to the closest VM, right? So this means that the networking layer, we have a software called the Fly proxy, needs to know data. It needs to know where's your app running, right? Is it healthy? Is it healthy enough to handle the request? What ports are open? Is someone making a request to the wrong port? Little details like that. And how it gets this data is also important. Like because it's factored into its routing decisions, right? If it's getting data late, it can't make the best routing decisions. Basically, it's going to be suboptimal. So just like a pictographic overview of what I've just said, we have edges that announce, same IP address. Your app is actually running on a worker. And yeah, the users get routed to the closest edge, and then the edge routes you to the closest instance. So we need to be able to read and write data pretty quickly. If someone creates a machine somewhere else, but a user is making a request from a different region, it still needs to know that data to be able to make its routing decisions. So at first, we used Consul, right? We put data in this key value store. For those who don't know, Consul is this distributed database service discovery platform that is created by HashiCorp. So it uses Raft as a consensus protocol to agree on the log of changes that's been made in a cluster. So you run like a cluster of 5 or 7 nodes, and they agree and communicate. This worked, for a bit, but there are some issues with this, right? So, okay, there are some issues with this because the cluster ran in like a region IAD, which is in the US. Every other region, Tokyo, Japan, needed to like reach out to it and pull that data. It wasn't very scalable, right? Basically how that kind of worked was that there's a tool called Consul Template RB, which is like written in Ruby, that can make updates to a file when the data in console changes. So we basically had it updating a JSON file, and then we had the proxy read from that file and like load it into its state. So as things were happening much quicker, like, as we got bigger, we had more users, so it was reading that file a lot. It's JSON, it has to deserialize data into its own internal state. So, it got unwieldy. So then we had a tool we call Attaché, right? Attaché ran on every node and tried to eliminate the problem of, reading the data from the JSON file. So instead, a separate process called Attaché would pull data from console. So console, you'd have an agent running on the node, but there's also like a central API, which is where you get like updates of everything. So it needed to pull the central one, which still had the problem of you needed to reach out to like the cluster in IAD, request needed to go there, and then it would pull it, and it was running on every node, basically, and it would insert that into an SQLite database, and then the proxy can then read from that. So it still had these problems, lots of latency and lots of data being pulled because each attaché was kind of trying to pull the same data from console. We have like 800 nodes, so imagine 800 processes trying to pull the same data right into SQL, each of those reading. So we had to step back and like look at the problem. And in the end of everything, to solve it, we created our own, I've gone over this. We created our own platform that we call Corrosion. So Corrosion is like a distributed system that replicates SQLite data to like different nodes. So each node has, of course, an SQLite database. And then when changes are made to that node locally within the cluster, it would disseminate that information to other nodes within the same cluster. So because it's eventually consistent, and of course, if you're going to replicate data, you have to handle conflict, right? We use cr-sqlite for conflict resolution using CRDTs. I'll go into this a bit more. We also, because we need to manage members in the cluster, like as nodes will come up, go down, lag behind. We use fork, which uses a swim protocol to manage cluster membership. And we also periodically synchronize with each of the other nodes. So this talk is basically looking at how Corrosion works and how it achieves low latency, replication of data across a large number of nodes. So just some features of Corrosion. So we provide an API or a PG endpoint too, if you want to. So we have a HTTP API, so you can make a post request, with the SQL statement that you want to run, and it will do that. We have you'd have to give Corrosion the schema that you'd like to run of the tables. It needs to know about the schema too. So you could make updates on the fly. You kind of don't need to pause Corrosion to do that. It had on the fly updates. This is HTTP streaming subscription. So because we had this platform component, the proxy, that needed updates, right, as it was being made. So we have subscription-based SQL queries. This means that you could like subscribe to an SQL query, and then Corrosion will send you updates as changes are being made to that query. Like if the data that the query would return changes, Corrosion will send you that update, so you kind of don't have components sort of constantly reading the database. Yeah, the propagation of states is basically talking about replicating data across the cluster, and we use quick transport protocols. So not UDP, not TCP, it uses quick. Yeah, we already kind of talked about this. We make changes using SQL statements through the HTTP or PG endpoints. So just a little about CRDTs because it's kind of central to how Corrosion works. CRDTs are a data type in distributed system where you can make updates independently to replicas, right? And sync them. And when they sync, they have a mechanism, or the data type itself can resolve conflicts, right? The order of changes don't matter. This means that the replicas don't really have to agree on like the sequence of updates. They can just have changes made to them independently, concurrently, and whenever they exchange their states, it could be the entire state, it could just be the operations that have been run on each of those replicas, they would eventually converge to the same state. So this kind of, an example I like to use is like counters. Say you had like counters running on like different nodes everywhere, right? If you decrement the counter, like this is an operation, right? It becomes 2 somewhere else, and this other one has like 2 increment operations, it becomes 5, right? Whenever or whatever order they exchange that log of operations, they'll still get the same state at the end. They kind of don't need to agree, okay, we're going to do a decrement first and then increment later. Even if you get like the increments, because there are 2 increments, because 3 minus 2 is 5. 3 plus 2 is 5. So even if it gets one increment first, and however the operations are interleaved, it doesn't matter. It will converge to the same states. So of course, counters are much simpler data types. So you have something like a grow-only set, which is a set that you can't remove data from. So a set has no duplicate. So even if 2 nodes sort of insert the same data into the set, whenever they communicate, it will just be the same thing still within the sets. So of course, things get complicated as the data type changes, right? So there are different ways that this conflict get resolved within distributed systems. A very easy example is like the last writer wins, right? You could have like a timestamp operation between 2 nodes, and then compare the timestamps where whoever has the bigger timestamp wins. So this is the last writer wins. So most times in this kind of distributed systems, you kind of need a way to resolve conflicts, and it can depend on the nodes communicating with each other at the point when you're trying to resolve the conflict or the order of changes. You kind of have to assume, although the changes can come in any order, any form, but you still have to resolve to the same state. So just examples of CRDTs, like distributed counters, like we've said earlier. A lot of collaborative applications actually use CRDTs behind the scenes, like Google Docs is like a very famous one, I'd say. So a lot of applications where you have like different people modifying something offline and later, they have to sync, tend to use CRDTs behind the scenes. So a lot, because you're letting people, you can basically make changes and then merge later. You're kind of picking the AP in CAP theorem. So CAP theorem is this theorem that says that in a distributed system, you have to pick 2 out of 3, consistency, availability, and partition tolerance. Consistency is like every node has the same data. Basically, if you make a request to 2 different nodes, you won't have like some discrepancies, right? Availability means, your software is available, people can make reads, people can make writes, and partition tolerance means, there's a networking, problem, and there are some nodes that can't talk to each other, and it's still functional. So basically, what happens when there's a particular partition tolerance, when there's a partition means that, the nodes keep on, doing the work locally, and whenever that partition heals, it'll just exchange data and they'll converge to the same state, but then the replicas might have times when they are not consistent, like before it receives states from other nodes. So it's kind of a choice that we've made in Corrosion. So Corrosion is built on top of this library called cr-sqlite. So cr-sqlite is an extension. It allows you to merge cr-sql databases together. So I'm just going to play a small video that I've recorded. 1 second. So let's just play it quickly. So sorry. Okay. So this is loading the extension, right? What cr-sqlite does is that it tracks the number of changes that's been made to a column within a row in a table in the database. So it has, each table that is in your database has like a second table that is tracking changes to it. So each time you make a change, it would increment something called the column version, right? So 1, if you make another change, it increments to 2, 3, like that. So when it's trying to merge data, it prioritizes, so it doesn't really use the concept of time. It prioritizes the rows that have had more changes made to them. So if this row has a higher column version, it would prioritize this node. So just to play a bit, just to see it in action, because it's easier when it's more concrete. So just creating a table and inserting values into it. So it has this virtual table where you can see the views. So it also has something called causal length, the CL in the table. So that also tracks like how many times the row has been deleted and reinserted, which is called like a resurrection in cr-sqlite terms. So just to pause it here, which is kind of what I'm getting at. So each time something is inserted into this table, right, this second table called cr-sql changes is updated, right? It tracks like the change to each primary key. This primary key is sort of like has been encoded. The primary key 1A, because A is the primary key in this table, has been encoded, right? So it kind of uses the primary keys as the keys in a map, right? And then it tracks, each column. So it tracks it at a granular column level, right? So if you are accepting changes from, say, it gives you this functionality, and we've built something over it to make it easy to communicate within nodes. But if you were accepting changes from a different node, you would insert it into this table. So before the insert happens, it would do this comparison, and that is how it determines which node wins. Right? So just to see, the column B has been updated. So its column version has changed, is updated to 2. 1 second, let me make this a bit faster. So when it's deleted, trying to just fast forward to where I made some changes, just to see how the decision goes. So this is basically, I'm trying to pretend, sort of run a statement where I'm inserting changes into the cr-sql data, into the cr-sql table, right? So the site ID is kind of an identifier for the node, right? So if it has a difference, I'm trying to change up the site ID so it's from a different node. I've deleted the row like a few times. You can see the CL is 3, so basically it prioritizes, if you've resurrected, as you've deleted a row, inserted it, you would have a higher causal length value. So basically it compares causal length first, then column version. And there are situations where this might be the same thing. Then it will compare the values, the actual value. So if you have an integer as the value of the column, the higher value would win. And lastly, we use the site ID as a tiebreaker. So this is just inserting things from another node inside here. I'm just tweaking things so it's not the exact same site ID. So for what I'm inserting, it has like the same column version. Sorry, let me just pause this a bit. So I was trying to insert something, but it has the same the column version is 1. That's the second to the last value is 1. So you can see that even though I've inserted something into the table, nothing changed, because with the cr-sql algorithm, it's basically rejected the change. Or not rejected, you'd say this change 1. But if we tweak the causal length to be much higher, say 7, not usually 5, okay, you can see that the one from the different node has 1. This just, and if you check the actual table, you'd see that the change has been made. So just to give you an idea of how conflicts are kind of resolved within tables. So basically it has triggers. On insert, update, delete, it would do this comparison first. So it's very possible that you would make a change that would not win, basically. So this is just tweaking stuff a bit, just to show more. So you can see, this is basically pattern. So you can see that because we've inserted a winning change into cr-sql changes, right? The table, the information in the table itself has changed. This is basically how cr-sql like works under the hood. So corrosion is basically like a wrapper around this. Sorry, 1 second. So it's basically a wrapper around this, right? So you make changes, people using corrosion don't really need to know about the cr-sql changes. That's what happens within corrosion. So you make changes to the table, using the usual SQL statements, inserts, updates, deletes, and those changes generate, the rows in the internal table, cr-sql changes. Then we broadcast those changes to other nodes. When they apply it, each of them, regardless of the order, right? If it receives, an old change that has like an older version, it won't win. It will basically just still retain the newest version that it has. So modifications to the table generates cr-sql changes, and each of those changes gets an internal version attached to them. So this is basically how corrosion tracks changes and communicates within each other, right? So first of all, we kind of prioritize like a local first. We broadcast the change to the nodes closest to us. We broadcast it a certain number of times. And those nodes will also broadcast to others. So this is like a gossip-based dissemination style. It's been written about a lot. Just a small animation to show you how the cluster spread, how the information spreads within the cluster. So, you send it to 3 nodes, and then those 3 nodes send it to 3 other nodes. And, it's basically like, it's also called like an infection style, because, it's kind of coined from how infections spread, right? You infect 2 people and they infect 4 other people, and, next thing, everybody's sick. So that's basically the protocol that we use when broadcasting changes. We broadcast it a certain number of times. We pick, the selection of nodes is random at size, the first one. We still select like n number of closest. We broadcast it first to like all the closed nodes, but we'll still broadcast it certain number of times. This is to ensure that like every node in the cluster gets the change. Up to a certain limit. So if a change has been broadcasted a certain number of times, at some point we would want to stop. If you kind of look at this, like one node broadcasting to 3 others, and then it kind of forms a graph. So you broadcast it, log n times, n being the number of course, not exactly log n, but something times log n. There's kind of some mathematics behind it to ensure that if you broadcasted a change, this number of times, you get across to all the members of the cluster. So another thing is, because it has a broadcast mechanism, let's say we are overwhelmed with changes, right? We tend to prioritize those that has been broadcasted less, because they are yet to spread as far as the others. So let's say there were like a lot of changes, maybe due to some issues, CPU, whatever, we're not just broadcasting as fast as we should, and we just have like a backlog of the queue. We could, we prioritize like changes that have been broadcasted less, so those ones get out too. So broadcasting is not our only mechanisms for getting changes out. We also have like a sync protocol between nodes, because the last level of nodes will get it slightly later, right? And we're kind of prioritizing speed. So occasionally, certain number of times, periodically, right, the nodes would initiate syncs with each other. So what this sync does is like the node, like I said earlier, like Corrosion will attach a version to each change. It has its own version that is tracking each change. So, this node will say, hey, I have version 1 to 5, what do you have, right? And the other node, so it will initiate syncs with like n nodes, and each of those nodes will send their own states, like, and this is what data they currently have. And then it will look at their state and say, oh, this node has version 1 to 5, and I have just version 1. That means I'm missing 2 to 5. So it would request what it has found out that it needs, basically. So it would do like a diff between their states and send requests for whichever is missing, right? So this is also like, broadcasting alone, the messages could get dropped, a node could also be offline, really, maybe it's down. So it's just really not even available to receive any of the changes during that time. So even if we have a lagging node that comes up, it would basically start syncing with every node at intervals until it comes up to date. So the sync is constant. We initiate it periodically. Just a bit more on subscriptions that we've talked about earlier. So we basically provide a HTTP API, and you can basically send a query, and we will send you updates, as there are changes to like the data that would have been returned to that query. We'd send updates. So basically, it helps so that clients of Corrosion don't have to like keep reading from database. Like reads, you can, because cr-sql, the changes that we make to the databases, you can read straight from, using normal cr-sql statements. But just to make it easier, we also provide an API where we can send updates. And how this works is, because when we receive data from other nodes, the row, if you see the row, it has like, the PK is like a compacted primary key. So basically, even when we receive data from other nodes, we kind of know what primary key has changed, just looking at, because that's basically, we just put that data in like a struct and send it out. So, the cr-sql internal table has like the table name, the primary keys, the particular column that the change is for. So we could just look at this, and then we run a modified version of the query for primary keys slightly, so it will be faster because we are checking for particular primary keys that we know has changed. So this is kind of what it looks like. So we send first the column, then rows. This is initial query. This is the first update. So the row is the initial, data. Then EOQ means, end of query. It's done. So change, subsequently, we send you updates for each one that has changed, like deletes, updates, inserts. So you could see how that could be convenient. We also do just updates, basically where we just send you what has changed. This is useful in, let's say there's a cache and it just needs to know what has changed so that it knows when to read from the database. Here we don't really send updates about the data itself. We just say, oh hey, this primary key, this is very light to do because we kind of know what primary keys have changed already. We can tell if it's a delete or an offset by looking at the causal length. So if it's even, I can't go back to video, but when the causal length is even, because at first it's 1, and if you delete the row, it becomes like 2. So basically deletes are even. So we can just, with the data that we've received, check if it's even or odd, and we would know if it's, a delete or an offset. So this can just be a notification for it to go read the database. So it doesn't need to just do it randomly. It can do it exactly when the data has changed. Just a bit about security within the cluster. We provide this TLS command for you to secure communications between each of them. Each would have the same certificate authority, and then you can generate certificates for the server. Just a bit on how this is running at Fly. So it's running on about 800 physical servers. The subscriptions are used by the proxy, basically to get updates on machines that has changed, health checks, all of that. It is not the source of truth, and what that means is that the data that comes into Corrosion is kind of already stored somewhere else and then synced to Corrosion, and Corrosion gets it everywhere. Like the FlyD, which is the component that manages machines on a node, has its own database, and then it would still write to Corrosion, but basically if something happens, we can kind of sync from the source of truth. It's kind of a weird way. Like Corrosion works normally, but we've kind of just evolved to use it like this. There's also like minimal conflict with the data because different components kind of own different parts. I'll say for something like the machines table, like where we store information about the machines, right? Each node kind of owns its machines, and each node will only update the data about its own machine. So there's kind of like minimal conflict resolution going on. So it's kind of, I think the thing with CRDTs is that they can be kind of surprising. So we don't have a lot of surprises because there's not a lot of things competing over the same role in a database. That applies to like most of the tables. There's just like a component that manages this and is solely making the changes there. So we have a lot of changes going on. It's in heavy use. Just the short graph about, just a graph. The P99 is like under a second. So it's pretty fast. It's the syncing and broadcasting, like there's always a lot of chatter going on, and nodes are mostly up to date and within a reasonable amount of time. So it's working well for us. Just some caveats. Is easy to shout about the good parts. We are bound by cr-sql constraints, right? It only works for tables with primary keys. So if for some reason you don't need a primary key in your table, which is not very often, Corrosion will work for you. If you have any unique constraints on a column that is not the primary key, also won't work. This is kind of central to how cr-sql works because it uses the primary keys to track changes. So if you have no primary key in your table, it kind of doesn't know what to do. We also, updates, on-the-fly updates work very well, but destructive changes, not so much. We kind of haven't ironed this out because, when the schema changes, right, we still might not have communicated it to the other node. So sending out those changes, it could be requesting for changes that are effectively gone, right? So destructive changes are currently not allowed. We kind of don't have any authorization or authentication. Like we do not authenticate who is accessing the HTTP API. There's currently no inbuilt mechanism for that. That's just something of note. So just some lessons learned. So we had to first of all, we started from console, and then we had this thing that was kind of still bound to console, like it pulled from console and puts it into SQLite. We had to take a step back and think of what are we actually trying to achieve, right? Even though we were using console and it was kind of working for us, because we had stayed with console, we were kind of sort of thinking of the problem from that angle. We had to step back, what are we trying to achieve? We want to be able to read and write data pretty quickly, and is there another easy way for us to do this? I didn't talk about this in the slides, but Corrosion also has what we call Corrosion console, Corro console. Basically, because the services API has a particular schema, basically services and checks. Consul has services and check. You can pull, their API to get updates on that. So basically, what Corrosion Console does is like it pulls the data from console, but this time locally. It doesn't need to pull the central data because each node kind of pulls its own local agents, and this is basically like the next step. The evolution of the problem is like it pulls its own local agents, which is it's not reaching out to the cluster in IAD, and then inserts it into the SQLite database, and then that gets like replicated to every node. That's basically how we solved the original problem of getting data from console, even though right now we do not use console for health check. We've kind of phased that out, but we still had a period of time where console is still being used at Fly, but just not in like this. It's not like used for health checking and like storing data. So we basically had this period of time where console was still being used for health check, but we kind of solved it by having Corrosion, Corrosion pull the console HTTP API, which is kind of what Attache did, but the difference is now we're just pulling only the local agents for its own service. So by the time every node is pulling its local agents, which is quicker, doesn't have all those lots of bandwidth, and then it inserts it into Corrosion. Then Corrosion would then disseminate that information around the cluster, so every node would eventually have a global view of the services in the cluster. So something else that you need to be aware of, especially when dealing with gossip-based system, is something I call the broadcast storm, which is when like your cluster doesn't, probably due to an edge case, it doesn't stop propagating changes, right? We had this incident with Corrosion where because some changes failed to apply, we had a cache, just like a map that just marks like, oh, we broadcasted this change before, right? But that map also signified the failed changes, right? So when it changes, it signifies applied changes. So when a change failed to apply, we would take it out of the map. So we received some changes, broadcasted it, put it into the map so we know that we have broadcasted it, and then we'll try to apply, and then applying those changes failed, and we'll remove it from the map. So the change might come in again because we select nodes randomly for broadcasting. So a node can be selected twice. Like you could keep getting the same number of changes because the selection is basically randomized. We don't know what node has already seen the change. We'll just select n, and the broadcast contains the number of times it's been broadcasted, right? It just has a counter. So basically when you receive the change, you increment the counter, select n nodes, broadcast again. So when it receives the change again, it would, it's no longer in the map because it failed to apply it. It would broadcast it again. So we basically had this situation where the nodes just kept broadcasting things to each other, flooding the network links. So just when you're dealing with gossip-based systems, it's always good to be careful about like what you're broadcasting. Is there a point? Basically, you're careful about the point you should stop broadcasting it and how something has already been broadcasted. Okay, another thing is, don't forget the delay, right? As much as Corrosion is quick, I think occasionally it still catches people by surprise when they're like, oh, I inserted this thing into the SQLite DB and it's not instantly available. I think eventually consistent systems are slightly harder to reason about. So build your systems to be resilient to the delay. So for the proxy, it could receive a request for a destroyed machine, but it hasn't gotten that update yet, right? So when it routes it to the worker node, that's where the change is originating from. So it knows that the machine is no longer in existence. It will basically say, oh, I didn't find this machine. And the proxy knows to route it to another healthy machine. So basically, you also have to build your systems so they still make optimal decisions when they have stale data. Corrosion is relentless. It's like you could delete, if you insert bad data into Corrosion, it would quickly disseminate it. You could delete it, but it's just like something to be aware of. It's like, this is constantly, you can't have a table in the corrosion schema. You can't have a table in, the SQLite database that's not managed by corrosion, but you kind of can't have like roles that aren't, it disseminates everything. Yeah, corrosion is open source. You could take a look at it. It's written in Rust. Rust is becoming the go-to systems language, I'd say, because of its memory safety and how much the compiler helps you to write the right thing, I'd say. So it's open source. You can give it a look if you're curious. Yeah, just a lot of what corrosion does is not particularly new. Things have been written about it. I didn't go very deep into this because I thought I won't have enough time, but we use the swim protocol for membership, which is basically how we track what nodes basically join and leave the cluster. Nodes don't need to, basically corrosion will keep going as nodes join and nodes leave. It just needs to take care of that. So if it thinks a node is down, it won't select it for broadcasting. So we use swim protocol for for membership management, and cr-sqlite, CRDTs. All of these are just like interesting parts of corrosion, and you can take a look at them if you're curious. Thank you. I guess that's the end of my talk. And so if you have any questions, that would be great. Oh, yeah, sure.
You mentioned that this gossip algorithm and synchronization between the nodes, what happens if the node gets outdated? For instance, it's not active for some time.
Yeah, so basically it would be still, it would have the wrong data. Whenever it comes online, it would start syncing again. When the node is outdated, right? Maybe due to networking issues, other nodes would probably notice, right? It would say, okay, this node is down. We can't depend on it to keep broadcasting the rest of the changes. But what happens over time actually is that the node is just out of date, right? The cluster would keep going on, but that node, whatever is trying to read data from that node would get an outdated data. So we actually kind of alert on this in a way that we kind of check the deviation between the number of rows on different nodes and alert on these. But this is something you have to take care of. You have to be aware that corrosion won't really scream if a node is behind. It'll kind of just leave it. It'll just be like, okay, we'll keep matching on. So it's actually maybe a caveat of corrosion because that node, whatever is depending on the data in that node would be actually out of date. But whenever it comes online, for whatever reason, because normal operation is supposed to be syncing, it's supposed to be broadcasting, so maybe there's a networking issue or, corrosion is just suffering on the node, maybe because there's just the node is overloaded, right? Whenever that heals, automatically, it would send a ping out, other nodes will know that it's back. It would start syncing with other nodes. So it would lag behind, but it would also be able to recover on its own soon enough, if it's not for an extended period of time. But yes, even if it's an extended, it will still be syncing. It just might take a while to catch up. Does that answer your question? Okay, thank you.
If data is synchronized based on a column version, how does it work across transactions? Like if I update few columns at the same time, is it possible that it will synchronize through different nodes, partial transactions?
So you're making a transaction to the local node, right? You would make it to local corrosion. So because it's in a transaction, the change to cr-sql would only happen after when the transaction succeeds, right? If the transaction is rollback, maybe there's something. cr-sql won't get that. It won't have the backup chain roles, basically. So when you make the change to the local node. If the transaction succeeds, it would have those changes. If it didn't, it won't.
Yeah, but if I have them, is it possible that the other nodes, if I have them,
Oh, yes.
is it possible the other nodes will only see part of?
Yes, it's possible that it's out of, maybe it gets the changes for one table before the changes for the other. Yes, we do not recognize the transaction within Corrosion. We do because we tag it with our internal version, right? And we propagate all the changes at once. They would all have the same internal version. So when a node says, oh, give me version 2, we would send you everything, which would have the same version because they are within the same transaction. So that's basically how we work around that. So there's no inbuilt like cr-sql transaction, but just by virtue of how Corrosion communicates, if you say, give me version 2, the version 2 would be tagged like all the rows within that transaction would have the same version within Corrosion.
Even across tables?
Yes, even across tables. The version is different from like the tabular one. So we would batch all the related changes to one version together and send it across. Okay.
How do you approach testing this?
So we have integration and unit tests. Basically, we have like integration tests that kind of, starts off Corrosion. You can, all our tests are also open source. So we just have like integration tests, insert data into, different nodes. We just start off different processes. That sort of mimics different nodes. We're actually looking into testing this more, but our tests are kind of like, the normal tests you would expect. We kind of start off different processes, insert into both of them, check after some time, I'll let them sync. After some time, check that they've synced and they have the same data, at the end of it. So that's, aside testing, a lot of the other smaller components, right? Like the unit tests, are we incrementing correctly? Are we checking version? Are we checking gaps, right? Because if, let's say I've received version 100, but the last version, the greatest version I know about a node is version 80, where I receive 100. Like, are we tracking the gap? So I have a gap of like 81 to, are we tracking the gap correctly? Those are things. So those small ones have their own unit test, but we also have integration tests. And we're looking into testing more. So you can check it out too, okay?
Hello. You mentioned that you are still using Consul to do the health checks. Do you plan to actually retire this part? Or you
yes,
always
it actually has been retired. I mean, like that ran for a while. It was just retired recently. We now have like something local on the node that checks the health, because the machines are already running locally on the nodes. But it's still, what the new component still inserts into Corrosion, and that's how that data gets everywhere.
Cool. And then the next question is that if you're retiring Consul, do you plan to offer the DNS interface so that you can also do service discovery via DNS on Corrosion?
Well, it's not in the roadmap right now. Like, we have something called, we have a DNS component that also depends on the data for Corrosion. So I could see that kind of working, but it's deeply tied to the schema of our tables, right? Corrosion by default doesn't really come with schema. You define the schema yourself, so it's very flexible like that. Whatever you want to insert, however, whatever your table looks like, it would automatically, accept statements into that table and disseminate the data. So the components that we have, it's wired to basically how our data is set up, right? Because we have like something called .internal. So you can say your app name .internal, and we would give you like IPs of your app, right? But is looking at Corrosion's data, but it's deeply tied. So we don't have something like offering right now, right? What I would say is, if you want to disseminate console data quickly, that one, because Consul's API is kind of fixed, so that part of Corrosion kind of would create the services table, checks table, and insert that for you. So that's what, if you have like a not random, but it's like if you have an SQLite database that you've been meaning to scale, and trying to turn it into a distributed application. Corrosion is something that works very well, but we don't have that DNS feature yet.
Brilliant. Thank you very much. We are at time. Thank you, Somtochi.
Thank you.